Hello everyone. I'm going to start to try to update my back catalog of SMO solutions. And so that will start with the SMO Open from 2020. Right now, if you're watching this, depending on what section you are focusing on, for the SMO Junior and Senior, the papers up to 2020 solutions exist, and for Open back to 2021. So I'm doing 2020 Open for a couple of videos, and then we may step back a little bit further to 2019, 2018, and just let's see how much time I have in the coming months. The first thing is that I am not saying the SMO Open Round 1, I am just saying the SMO Open 2020 because in 2020 that was back to COVID, right? Feels like a long time ago. It was back to COVID, and so there was no Round 2 at that time. The SMO Open was only Round 1, and the same for Junior and Senior. So this is the SMO Open for that year. The difficulty was not especially high. It was just Round 1 only, and then there was no time to have Round 2. So it is perfectly good practice if you would like to do a SMO Open Round 1 dry run and you have not seen these questions before. I've included a link to the questions in the description below. You can try it on your own first. Alright, so if you are about to do the questions, please pause the video. Otherwise, let's get started. We will go through about half the questions in this video. Question 1. If S is the sum of all the real roots of the equation x squared plus 1 over x squared is 2020 squared plus 1 over 2020 squared, find floor of S. Now, this is not a very difficult equation to solve because it's not a very difficult equation to guess the solutions. So the first method is just to solve it by observation. Now, we realize that of course x equals to 2020 works. So does x equals to 1 over 2020. So does x equals to negative 2020, and so does x equals to negative 1 over 2020. So all of these clearly work, and that's actually it. We know that's it because if I were to multiply by x squared to everything, you will get a degree 4 equation, which means that there are at most 4 real roots anyway. So if there are at most 4 real roots and we have found the 4 real roots, that's it. The sum of roots is 0. Which is something that in retrospect we can see is quite clearly true, since this left-hand side is an even function. Now, whenever we are asked for the sum of real roots or the sum of anything, there are two possibilities. The first is that the SMO only can ask you for one answer, and so if let's say the roots are 2, 3, and 7, then 2 plus 3 plus 7 is 12 is quite an unlikely thing to coincidentally discover. But the second reason is that sometimes the sum is easier to get than the list themselves. The list of roots itself is harder to obtain because the roots follow a property that allows you to get the sum immediately. So even function means that if alpha is a root, then negative alpha is also a root. And so you can pair them up, and if you can pair them up, the sum is 0 without even requiring us to find the solutions themselves. Question 2. Now you see there are the floor and ceiling functions down here in question 2. In the actual SMO paper, this would be on the cover page or in the question itself. So it will either be in the cover, they will say, oh, this floor function here is the greatest integer that is less than or equal to x. The ceiling is the least integer that is greater than or equals to x. This will be mentioned explicitly, so don't worry if you don't know what this means, right? It will tell you, in short, floor x basically means round down, and the ceiling of x is just round up. Of course, if you already knew this, then rest assured that this notation is standard, it's not going to change. Find the largest positive integer x that satisfies this equation. However, means that this is pretty much redundant for this question, because if it's a positive integer, then this is doing nothing, so they are really just confusing you a little bit. The floor and the ceiling is to round up and round down to the nearest integer, which is redundant. You are looking for integer solutions x. So really, you can just throw this away. In fact, these are both x. So that's all you're left with. Once again, this is now a quadratic. So like question 1, it's possible to just observe that 2020 and 2030 work. So those are the two roots of the quadratic, and the answer is 2030. In this case, if let's say that you are not sure how to do it, it's okay to sort of list starting from 2020, then look around it until you find 2030 or vice versa. Since we know that we are looking for a positive integer answer, it's okay to list and guess. It's also okay to expand it out, just that the numbers will be a little bit more complicated to work with. Question 3. This is something that is unique to the SMO Open, which is that this is sort of the A-level problem. Now this is sort of the A-level problem, and for those of you who don't have Olympiad experience, the first time where it will be explicitly tested is at the A-level stage. If you have Olympiad experience, you will look at this and say, this is a primary school Olympiad question, and you are also right. Some of the things in primary school are technically not in syllabus up till A-levels. And so it is objectively simple as an Olympiad question. It's also a standard A-level problem. Of course, what A-levels would classify this is as method of difference, where the method of difference is in the special case of partial fractions. And so if you are doing this not as an A-level student, I'm sure that you will think of partial fractions because you have seen this many times before. And so on up to the last factor here. If you sum it, everything will cancel with the common factor of 1/2 on the outside. So n over 2n plus 1 is supposed to be equal to 0.48, and 0.48 is 12 over 25. So evidently this means that n is 12. Now I have to also add on a general statement, which is that because this says it is in the A-level problem type, it may not always be one that looks as familiar as this to those of you who have done primary school Olympiads and seen it already. Right? So this in general is saying something that of this form. Right? If you have 1 over a plus 2, then we know that if we were to write it as partial fractions, it will be something over a and something over a plus 2. And then by cross multiplying and comparing coefficients, you will find that it is going to be 0.5 and negative 0.5. This is straightforward, but you will need to go to your classic partial fractions methods. If let's say that you get something a bit weirder, like let's say now I've got 1 over x, 2x plus 1, 3x plus 2, or something weird like this, if you had to go and try to simplify it, you will need to go to the full-fledged method, because none of us are going to know how to simplify this just off the top of our heads. Right? So you would need to solve this on your own, but for a question like this, if you recognize the pattern already, then you just use the pattern. Okay. Number 4 is also an A-level style question, except that it is an A-level style question which would be considered as a difficult A-level question. It would be also considered as a tricky Olympiad question if you have not learned some amount of either vectors or linear algebra. Now here we're told that the 3 planes have a common line of intersection. Now 3 planes have a common line of intersection is not going to be the usual situation. Now it's not the usual situation because if we think of what intersections are just solutions to a bunch of simultaneous equations. And so if it's a line, that means that there are infinitely many solutions to the simultaneous equations. That's not usually the case, and so we should know when we are solving simultaneous equations, the usual thing that will happen is that you're going to eliminate the variables one at a time. So we treat this as equations to be solved, not worrying too much yet about the planes or the line of intersection. And if that's the case, what you would do is just to say, I will eliminate, let's say, x. So if I take 2 times of equation 2 minus 3 times of equation 1, to eliminate x, I will get negative 2y minus 14z equals to negative 3. If I were to take equation 3 minus equation 1 times 4, this will also eliminate x. I will get negative 2y plus a minus 24z is equal to b minus 20. Now this is going to normally give me my values of y and z, because if I now subtract, let's say 5 minus 4, I am going to end up with a minus 10z equals to b minus 17. And so this would normally give me z. I put it in, I get y, I put it back in, I get x. That would give me 1 point of intersection. Unless it turns out that there are infinitely many solutions for z here. So there should be infinitely many solutions here. Otherwise, infinitely many solutions overall is not going to happen, because if I knew what z is, then I'll get y, I'll get x, just one choice. Now, infinitely many solutions to a linear equation cannot happen, to a one variable linear equation cannot happen unless these are both 0. Okay, and so our answer, the question is asking you for a plus b is 27. Now take note that if you were solving as an A-level question, one of the things that you could do is to use the normal vectors to say that they have a common line of intersection. Means that the first 2 planes solve for the line of intersection, and then that line must lie on the 3rd plane, and so that line must be orthogonal to the normal vector of the 3rd plane. We can do something like that. However, I think this is definitely going to be the easiest way, whether or not you have a calculator. Question 5. Yet another A-level type question. Complex numbers this time. Let I be the complex number square root -1, n be the smallest positive integer such that root 3 plus I to the n equals to a, where a is a real number. Find the value of floor n minus a. Now, once again, another A-level type question where it depends on what you know. Now, the A-level approach would be to convert root 3 plus I into exponential form. If you convert it to exponential form, you're going to get the most important part is the argument. Of course, we can also get the modulus of this. And so that means that it will be 2e to the I pi over 6. Now you want this to be a real number, means that if I just take this review, it is going to be n pi over 6 must be a multiple of pi. So the smallest n is just 6. And if the smallest n is just 6, a, which is this quantity, is 2 to the 6 times e to the I pi, which is negative 64. Okay, e to the I pi is negative 1. 2 to the 6 is 64. Again, with this very unnecessary floor function on the outside. You can just ignore that. The floor function doesn't really matter. Now, this is the A-level students' approach. But I want to say that for those of you who are taking the SMO Open, especially if you're watching this video a number of months after I released it, and this is 2 months to whichever SMO Open that you're about to do, don't worry about learning complex numbers from scratch. Neither do you want to worry about learning vectors from scratch, as we just saw in question 4. Just work with what you know. And so if, let's say, that all that we know is I is the square root of -1, then what you should do is simply to just list out the first few powers. Right, so this is sort of the low-tech approach. Plus 2 root 3i minus 1 is 2 plus 2 root 3i. That's not going to be a multiple of, not going to be a real number yet. So I can cube it by just multiplying root 3 plus I to this again. You get 2 root 3, 6i, 2i, and 2 root 3i squared, which is -1, and therefore cancels out to 8i. Now at this point we basically know that, okay, when I cube it I get 8i, and I squared is -1. So if I have the 6th power, it would just be a real number. Okay, and so likewise, this would also give you the same conclusion if you are not already familiar with complex numbers. Now, I strongly urge you when you're doing Olympiads to just not skip any question unless you completely don't understand what it is saying at all. Because sometimes Olympiads are built such that they want to give as many people as possible a chance to be able to solve the question just by playing around with the numbers. So please do that rather than skipping it entirely. You will be able to get the same answer without knowing complex numbers that well beforehand. Now, the flip side of this is that to some extent, you must also know when to skip questions. So I just said that you don't have to know it to do questions, but if you are looking at this and you don't really understand vectors, you are going to be really confused. Now, what we need to do is to find the area of the triangle enclosed by 3 lines, which are L1, L2, and L3. That just requires us to find intersections. Now, to find intersections, it means that for what lambda, mu, and nu will these coincide? And it turns out that it is not very hard to eyeball. L1 and L2 will intersect at 4, 5, 6. For I plus 5j plus 6k. It's also not very difficult to eyeball that these two intersect when mu and nu are both 1, just by looking at the coefficients. That would be 7, 4, 4. It's also not very hard to eyeball the L1 and L3, since this is 4, 5, 6, this is 1, 2, 3. The difference is 3, and this is lambda, lambda, lambda. So lambda equals to -3, and nu equals to 0. The intersection is just 1, 2, 3. It turns out to be quite easy to find the intersections of them. So these are not necessarily going to be always nice numbers. In general, you would just need to equate them and solve simultaneous equations. But here, I think we can shortcut things a little bit. Now, these are your 3 points. I, j, and k are just the x, y, and z directions, as has been indicated in the question. And so, technically speaking, if you don't know any vectors, I said it would be very confusing, but still you have a chance, because these just correspond to coordinates. I'm going to call these points A, B, and C. And so if you were to do it without vectors, what you can do is just to get the lengths of AB, AC, and BC by Pythagoras. And hilariously, you will realize that this is a right-angled triangle. Right? Because 14 plus 27 is 41. So again, the question is trying to be nice. It is coincidental that these actually have a right angle there, and so the area is just straightforward. And question asks you for 10 squared. You can compute this, and the answer would be 945. But this is, again, just because the question is trying to be nice, and in most situations, the way to do this would be by using the vector cross product. Okay, so the vector AB and the vector AC. if you're not familiar with the cross product, then the way that you would do it is by what has been written on the other side. Three minus 6, negative 3. 6 minus negative 9 is 15. And negative 9 minus 3 is negative 12. So half times the square root. Can factor out a 3. Okay, and this is again the same as that. But it works in general, not just in the situation where we're fortunate enough to have a right angle in our triangle. Okay, so far you have seen a bunch of questions which I keep saying are A-level type questions. If you are an A-level student preparing for the SMO Open, you should think that this is quite good news. If you are not an A-level student, you should also see the good news, which is that there are ways around it as long as we understand the basic vocabulary, right? Which is why doing these past questions is useful to just help us to understand the vocabulary of the questions, what they're trying to say, and the theory of it. Don't prioritize it for now. Learn it if you have time. If not, focus on the intuition first. Question 7. Now this is a functional equation. It is a functional equation which has a very obvious looking solution, because a squared minus b squared equals to a minus b times a plus b is an identity. So we know that fx equals to x works. Well, except for that. Okay, and so let's talk about the strategy for these kinds of functional equations in round 1. In round 1, just guess the solution if you can. And you guess the solution by starting with something that roughly works, like fx equals to x, and then adjust it in the direction that is okay. Now, what I mean by adjust it, now, if I use fx equals to x, f1 is 1. So you should try to adjust it to here via either adjusting by addition, subtraction, multiplication, or division. Now, I definitely cannot just make the function subtract a random number. However, because f appears on both sides, like this, if I were to scale it up or down, it will still satisfy this equation. And so I can say that, in fact, fx equals to x over 101 also works, because it's the same thing with over 101 on the left and right hand side. This will make our answer simple. There are just 50 pairs that add up to 1 each time. For the 4th or 5th question in a row, let me now explain how we would prove this and how we obtain this in the more universal and the more precise, rigorous fashion. The first thing, right, so justification, how do I know that there's nothing else? The first thing is that if I let a equals to b, I get f0 equals to 0. Now, if I were to let a equals to negative b, which is another way of making this 0, you're going to get, okay, so a is negative b. Just means that the fa and the f negative a are negatives of each other, i.e. f is odd. how is this going to be useful? Very simply, it allows me to kind of just jump through all of the integers as follows. I would like to essentially get myself an equation involving f of 1. This is f of negative root n. I move the negative to the outside. And if I rationalize this, this is what I get. Immediately, since this root n plus 1 minus root n is going to be able to give me a lot of values, oops, sorry, I forgot to I'm not actually writing this right. Okay, let me put my brackets in the correct place. I apologize. This f of root n plus 1 minus f of root n looks like this. It means that if I were to just run through all my integers n, I get this whole bunch of things, which if I were to just add them up, will give me pretty much any nice value straight away. Right, of course, f of 0 is 0. So for any positive integer k, this is true, and therefore in particular it would be true that if I put in k as m squared, f of m equals to 1 over 101 of m for any integer m as well. Right? So this is going to confirm that at least for the values that I'm asked to find, this is true. Now, there are lots of ways of justifying it, and you should probably use none of them during the SMO round 1. For round 2, this sort of thing is one possible way of handling functional equations. Just throw in all kinds of values that seem to be relevant, and then once you think that you have no other special values, throw in something that is relevant to whatever you're trying to find, if you're asked to find something specific. If you're asked to find a function in general, then of course we'll need to do something a bit different. Okay. Question 8. Find the sum of all the positive integers n such that n to the 4 minus 4n cubed plus 22n squared minus 36n plus 18 is a perfect square. I don't see much here immediately. I don't really see much that is going on, but it asks me to see if it's a perfect square. So I would like to try to complete the square. This is a fourth power, but completing the square is going to kind of give me a similar logic anyway. So I'll start off with this part, and I complete the square with n squared minus 2n squared. That takes up the first term, the second term, and 4n squared, leaving me with 18n squared minus 36n plus 18. Now, I realize that this is perfect for my attempt to complete the square because this has a factor of 18, and so I can complete the square with n squared minus 2n as the variable. And this is going to be my perfect square. Let's call that m squared. Of course, for about 1/3 of you, you may be wondering, why complete the square? The answer to that lies mostly in the SMO Junior. You see, a lot of the Olympiad ideas are scaffolding on each other, and so normally in the SMO Junior, the question will be, here is some weird quadratic, how do I make this a perfect square? And you would complete the square with the purpose of being able to get a difference of squares. Now, the same idea actually just has applied in this degree 4 situation, except that completing the square for degree 4 is not really a fixed process, we tried. So we tried and we succeeded, and so this is the result. We get a difference of squares. And since the n squared minus 2n plus 1 itself is going to be more than 8, this factor here is going to be also more than or equals to 8, since we can assume perfect square means I can take m as non-negative. That means I just can list out the possibilities, which is 9 and 7, 21 and 3, 63 and 1. Sum and divide by 2 will give me the n squared minus 2n plus 9. Subtract 8 from all of these, and that would just give us n minus 1 is 0, means n is 1, n minus 1 is plus minus 2, so you get 1, and 3, and well, negative 3 I don't include since the question asks for positive integers only. I also don't include 24 because that's not a perfect square, so in fact there's no comma, it's just 1 and 3. That was pretty anticlimactic, right? N is 1 and 3. You mean I did all this and it's just 1 and 3? I could have just guessed that. Yes, you could have just guessed that. Every question that asks about positive integers, if you don't know how to do it, try the small values. If it says positive integer, try 1, 2, 3, 4, 5, and 6, 7, 8, 9, 10 if it's still small enough. If it says integers, then try minus 5 to 5. Try some small cases, and that will give you a chance of guessing the correct answer. Because usually for such questions, it is very hard to make one surprise large positive integer work. How do you think they'll set a question up where suddenly 2024 or 2025 works and nothing else? That's pretty hard. So this is a trick for guessing positive integer based questions. Try the small ones and see if there are enough of them that you can just guess it to be nothing else. If it feels that way, put that down. Question 9. Now, this is yet another SMO Junior inspired question that has been pushed forward by several orders of magnitude of ugliness. Now, the first line is kind of a very common setup to a problem, except that now they have thrown in m, and then now they put in a difference of squares, they put in this power, so everything is just there to make things a little bit more scary. What I want to understand is just how is the inequality related to the identity above. And the difference of squares, which I saw a question ago, is going to almost always be useful to factorize, because it will be the sum, which is everything of all the a's added up together, and the difference, which is the alternating sum. Now, here's the lowdown on these sorts of equations where it looks like there are a bunch of coefficients and nothing else. The unspoken fact is that if I tell you they are the same thing, it just means that this is expanded out going to look the same as that. And therefore, it is going to be for any x. It says assume that these are equal. If I were to say that these two people are brothers, that's not going to be when are they brothers. Brothers are always brothers. This is not they are friends. Normal equations are like friends. They are friends only for a while, they may not be friends forever. Right? So x equals to 3 is not always true. It's true for this question maybe. But for this statement like this, it means that these two are the same for any x that I want to put in, and I can extract these out by putting in the appropriate x to make them appear. So to make this all appear, I just let x be 0. To make the negatives appear, I put x is minus 2, because x plus 1 is minus 1 is going to lead to the alternating plus and minuses. And so immediately you just put them both into the inequality, and you get 2 plus m to the 2019, m to the 2019 less than or equals to 2020 to the 2019. It's a bit of a silly question. Can I just cancel off the 2019 from both sides, or is there a problem? If you said, of course we can, then just be careful. The reason why we can actually do that is that this is an increasing function. When the 2019 power is an increasing function, yes, you can chop it off on both sides. If the 2019 was replaced by 2024, you cannot do that, because if it were 2024, then you need to worry about positives and negatives, because it's not just increasing throughout all real numbers. So be careful. What allows us to just throw it away from an inequality is that 2019 is odd, essentially. Now with that being obtained, then just complete the square, and this is less than 45 squared, so the maximum m is 43. I think we can stop at question 10. So our last question, we have got a limit, a summation, and assert. This is going to be the last for now of the, I've called A-level type questions. As far as I can tell, we will end the video on question 10, but for the rest of this paper, I don't think we have any problems that I would objectively consider to be A-level type questions anymore. Does that make the questions in front easier or harder? Honestly, I would say easier as long as you know what they mean. Because the limit as n goes to infinity, if you don't know how to do this, there is a floor function. You can test it out by using some small cases. As long as you know that this means a limit as n is very big, And this means add up from k equals to 1 to n. So let's say that you try n equals to 1 just to see the starting. And of course, that's not very representative. Just one term. This means square root of 1 times 2, right? 1 over root 2. That's not a lot. Yeah, 1 over root 6 plus 1 over root 8. Now that's still not very big, right? That's not very big because these are both between 2 and 3. Which means that this is between 2/3 and 1. If I take 3, now this is 3 point something, this is 3 point something, this is 4 point something. Again, you can roughly estimate that it is somewhere between 3/4 to 1. At this point, obviously, if we were to look at it and say it's very close to 1 but slightly less, and this is going to be true for the most part, right? Because in general, 1 over root n plus k is going to be less than 1 over n. You're multiplying n things that are slightly less than 1 over n. That means that s is less than but close enough to 1. That this should be just about 2 point something squared, where it's as close as possible to 3. Specifically, slightly less than 3 squared. Which is 8. The latest of unintended solutions in the first section of this paper. The intended solution is that this is actually a Riemann sum integral. A Riemann integral. Now, let me write it down one more time below. This is actually a Riemann integral, and a Riemann integral is in this form of a limit of a sum. And what is it the sum of? It's supposed to be the sum of the area of rectangles with 1 over n. This is the default setup. So in order to make it into the sum of infinitely many rectangles of width 1 over n, I should factor out 1 over n from here. Okay, I'm going to leave it in the summation notation for one more step. Now, what you must understand once you've set up this is that K over N is the correct form. If I let fx equals to 1 over root 1 plus x, so that this is going to be my sum, then this is what we want. What we want is this. If I were to draw the graph, I'm not even going to think too hard about how the graph looks like, except that I know that it starts off at 1 and then it goes down towards 0. So I'll just draw it with no significant resolution whatsoever. If this is at 0 and let's say this is at 1, then f of 1 over n, f of 2 over n, f of 3 over n, and so on, is the area of many small rectangles where all of these heights are f of 1 over n, okay, I'll just get f of k over n for k equals to 1 to n. Those are the heights, and the widths are 1 over n. And so therefore what you want is the area under the curve, which is where the calculus part comes in. The integral of 1 over 1 plus x and so you substitute it in. This is s plus 2 squared is really going to be equal to 8 as n goes to infinity. A couple of things before we end. The first is that we realize there are lots of workarounds, so don't be afraid to tackle the SMO Open. If you're watching this out of curiosity and you are a Sec 2 or Sec 3 student, don't be afraid to try the SMO Open. You may not solve a lot of questions, but just because you have not learned some of them before doesn't mean that we don't have some sort of estimation tricks or some sort of like special cases that make these questions doable for us. And the second point is just that SMO Opens look very different from year to year, because this year in 2024 there weren't so many of these types of questions. Do try these questions on your own. In fact, for any of the earlier parts of this video, if the screen was cut off at the top, please look at the attached questions paper. Try the questions on your own as well, and then just look at the video for whichever problems are new to you. Okay, so thanks for watching. We'll be up with the next two parts of this 2020 Open Paper Review pretty soon. So bye for now, and see you again then.